here's what we have. First of all, looking at this first graph, what kind of function is that? Like if you looked at that and I said, name that function, what would you say? Okay, y equals x. Okay, that's very specific. I'm going to say that's a linear function. That's what I was going for. You didn't really know what I was going for, so I'll give you a break there. But this is a linear function. It's a line. Okay? So we have a line. The parent function, Clay already said, the parent function is the most basic kind of line that you can have. And Clay said the equation of this was y equals x. What have we talked about in our class already with y equals x? It's just on your quiz yesterday. Yeah, all inverses reflect over the line y equals x. Okay? So if you got it wrong, or you didn't graph it right, that's what this graph looks like. So y equals x is the most basic kind of line that we have. What would you say is the domain of this line? Negative infinity to infinity. I'll just use interval notation here. Negative infinity to infinity. My graph goes left forever, it goes right forever. What about my range? Yeah, negative infinity to positive infinity. Both domain and range are all real numbers. That's going to be the note that we write underneath. Domain and range are all real numbers. Now, in a practical sense, because domain and range, at least what we're doing right now with domain and range, is kind of a theoretical topic, meaning that it's hard to like firm it up. You can't see it. You're not going to like talk about domain and range of a line in your everyday life in terms of infinity. But in terms of what we do in our class right now, that means that you can pick any number as an input. I can't spell input. So that means you can pick any x you can imagine, 5,000,000,002 if you want. And then you can get any real number as an output, okay? And that is true for any line that you're ever going to have. You can put any number into it and get any number out of it. Always domain and range of a line is all real numbers. Right? It's special and nice in that way. So that's one graph. You've been doing lines forever. Do you guys have any kind of name for that parabola? Starts with a Q. A quadratic. This is a quadratic function. The graph is called a parabola, but it is called a quadratic function. We're going to spend time with quadratics later this year. Well, do you know what the most basic equation of a quadratic is? Yeah, just x squared. That's the graph of y equals x squared right here. So that's our parent function. All right, what is our domain here? Yeah, negative infinity to positive infinity again. From left to right, we have an arrow in both directions. We're going forever left and right. What about our range here? What's our lowest y value? 0. Do I put a bracket or a parenthesis with the 0? A bracket. And how high up does it go? To infinity. Okay. So, a note about the parabola. It seems that our outputs, I'll say our y values here. Our y values, I can have 0, right? 0 is included, and I can have positive. What kind of numbers don't I get in this graph? Negative. So our y values are not negative. Right? At least for that parent function. So when you square something, you get a positive answer. That's what that's telling us right here. Okay? All right, so that's the second kind of function we have. The third kind of function we're looking at today is, if you don't know what this one is, it's a square root function. So this is a square root function. We are also going to spend time with square root functions later on this fall. I think this fall, maybe in the spring. I might be lying to you. It's sometime this year. Square root functions here. The parent function for this is y equals the square root of x. Now, let's talk about our domain here. Where do you start with your x's? 0. So I put a bracket at 0, and your graph goes how far to the right? To infinity. Okay. What about our range? What's the lowest y value? 0, and it goes up to infinity. So it looks like, do I have any negatives that I'm allowed to put into the function? Not for this one, no negatives over here, anything smaller than 0. And then all my outputs or my answers were also bigger than negatives, so non-negatives. So that's my note here. Inputs, which are your x's, and outputs, which are your y's. I know. You try talking and writing at the same time. They're all non-negative. You caught me, I'm human. I'm not a robot. So non-negative means 0 or positive values, so non-negative. And we have one more graph. I think these ones look kind of cool. We're going to get to these at the very end of the school year. This is called, there's two names we can give it. You can call it an inverse function, or you can call it, I'm going to put in parentheses here, a rational function. So this is what we're going to finish our school year with. It's also what you start pre-calculus with. So if you have friends in pre-calc, most of them are kind of unhappy right now, because these are hard. But rational functions look like this. The parent function is 1 over x. So we see a fraction already. Rational functions, rational means fraction. So it's lots of fractions. But it makes really cool graphs. Now this domain and range is a little bit trickier to see. All right, domain are my x's. Now when I look at this graph, see how there are arrows? First of all, the arrow doesn't go all the way to the left forever. Yeah, this one's easy. This one goes out to the left. But when I look at this part of the graph here, this is called, we don't have a word for it, or we don't know the word yet. It's called an asymptote. It's my favorite math word. This is how it's spelled. I can't talk while I'm spelling this though. Asymptote. It's my favorite math word. It's cool. So an asymptote is a line that you approach, but you never touch. So you get really, really close, but you never actually touch the line. So this green graph here is coming really close to the y-axis, but it never actually crosses it. Right? Now, let's look at this, and we'll figure out the rest of our domain. Same thing over here. This graph goes to the right forever. That arrow just keeps on going. However, does it look like on the left here? We have another asymptote. So it goes up, but it also never crosses the y-axis. So what x value, if we never touch it, do we ever get on that graph? 0. It gets really close to 0 from both directions, but it never gets there. So our domain this time is we're gonna write in set notation, because we can't really do that in interval notation. Well, we can, but x such that, I'll show you interval in a minute. X is not equal to 0. So you can pick any x, but x can't be 0. Now, if you wanted to write that in interval notation, you could do an interval for the left portion and an interval for the right portion. So you would say negative infinity to 0 with a curved parenthesis, not a square bracket. And then do union 0 to infinity. Do you remember that union symbol from last year? Yeah. That means or in math. So your x's are either on the left-hand part, which is all these negative numbers, not 0, or from 0 to all positive. So that's how you would do the domain in interval notation. Now the range is the same kind of thing. You get really close to the x-axis, but you never actually touch it. So how would you write your range in set builder notation? All the y's where y is not equal to 0. Great, so it looks like you can get any positive number, any negative number, but you cannot have 0 as an input, I spelled it right that time, or output. I was careful. So you can have any number, but 0 just isn't working for these inverse rational functions here. So we can find the domain from graphs. That's not too hard. Let's flip our paper over once you get that written down. Because there's a couple things, we're going to look at equations of functions today. And there's a couple equations that we need to be careful about. The types of functions that we need to worry about are these square root functions and the rational functions. So the last two. And today we're only going to worry about the domain of those graphs. So what can go in for x. The range, we're going to stick to looking at the graphs to find the range for right now. But we're going to worry about domain from square root and rational functions today. Okay? So square root functions. This, remember, was this graph, the square root of x. We have to make sure that only positive numbers and 0 fall under the square root. Because when we can you take the square root of 0? Yes, you can. What's the square root of 0? 0. All right, I can take the square root of a positive, right? What's the square root of 16? 4. Can I take the square root of negative 16? No. Well, you can, but we haven't taught you how yet. So we will learn that. You're going to learn a new number this year. A couple new numbers this year, actually. It'll be great. So for now, we can't do this because you don't have the tools yet. But at some point, you can. But for now, we don't like negatives under square roots. So the way we find the domain is we are going to set up an equation or an inequality here. You're going to look at what is underneath the square root, that x minus 6. That x minus 6 is called the radicand. The radicand is the stuff under the radical. You're going to look at that radicand, x minus 6, and you're going to say, okay, I know x minus 6, that whole thing there, it can be positive, so it can be greater than 0, or the stuff under the radical could also be equal to 0, right? Because we're allowed to take square root of 0, so we're going to say it could be greater than or equal to 0. Okay, so anything, that whole thing under the radical can be equal to a number that's 0 or bigger. So now we need to solve this equation for x so that we can figure out what inputs am I allowed to put into the function. So we're just going to add 6 to both sides here. When we do that, we get x is greater than or equal to 6. Those are the x values you are allowed to put in to this function. If I put 6 in, I get 6 minus 6 is 0. That's okay. If I put 10 in, I get a positive. If I put anything smaller than 6, I get a negative. Okay? So let's write this as a domain. Let's do set builder notation. Set builder notation, once I find this answer, is pretty easy. X such that, and then you just copy your answer. X is greater than or equal to 6. If I ask you to write interval notation, you might have to think a little bit. If you need to, some of us are visual, picture people. If you need to draw a really rustic number line, plot 6 on it, and think about how you would make a number line. Well, what kind of dot would go at 6? A closed dot. And if it's greater than or equal to, which way would your arrow go? Left or right? To the right. Okay, well that way it makes it a little bit easier for you to see how you would do your interval. You have a closed dot, so you have a square bracket. 6, and which way is the arrow going? To the right forever, to infinity, right? That would be the interval notation of that domain. So you should be able, we're going to ask you to do both. So you should be able to write the set notation or the interval notation. All right. Let's see. I want to say the right thing here. All right, we have another other function here. The rational function. Those are that 1 over x. Y equals 1 over x. We have to make sure that 0 is never where in a fraction? The denominator. 0 can never be in the denominator of a fraction. That's called undefined. So, the way we find the domain of this function is to figure out what number am I not allowed to put in for x. What number makes that denominator equal to 0? So we're going to set up an equation like this. We want to know when is the denominator not equal to 0. Because that's what we want. We want positive or negative. We don't want 0 in our denominator. So then we just solve this equation. We subtract 3. And we say, okay, well, x cannot equal negative 3. If I put negative 3 into the denominator of this fraction, I'm going to get 1 over negative 3 plus 3, which is 1 over 0. That's bad. That's the one number I'm not allowed to put in the denominator. You can pick anything else except 0. So if you want to write your domain here, we're going to stick to set notation with the curly brackets. You'd say we can pick any x where x is not equal to negative 3. That's how you would write your domain for this problem. That says you can pick any x you want as long as it's not equal to negative 3. Okay? So 2 rules for this domain today. If you have rational functions here, so if you need to, maybe make a note to yourself. We'll come back here. Well, yeah, I'll sit down here. For the rational function, so when you have a fraction, you use not equal to 0. You take your denominator not equal to 0. The thing to remember, when you're using the square root functions, you're going to take your radicand, greater than or equal to 0. You're going to compare both to 0, but 2 different symbols. Okay? That's what you need to remember for today. So let's do a couple practice problems, then we'll be all set. So to start here, these are all rational, right? These are the fractions. So every single one of these domains, we are going to find and set them not equal to 0. So the first one should be pretty simple. 3x plus 10. We take that denominator, set it not equal to 0. What number is not allowed to go in for x into this equation? Now, I didn't talk about the numerator. Do you think that 2 is going to affect anything? No, it's actually not. The 2 means absolutely nothing in terms of domain. You can just ignore the number on the top. So we solve this for x. We subtract 10 from both sides. That 3x is not equal to negative 10. And then divide by 3. So when you write your final answer here, you have to use, it says set builder notation in the directions. Up here. So, here's a pen. You do your x, because we're doing domain, such that x can be any number but not equal to negative 10 over 3. That is your domain. Any number but negative 10 over 3, which is negative 3 1/3. Now it should be pretty straightforward. Then we get to something that looks like b. b looks a little funky. X plus 3 over and x minus 2 is your denominator. Well, we're going to start the same way. We're going to take the denominator, x plus 3 times x minus 2, and set it not equal to 0. Well, that should look semi-similar to something you did back in Algebra 1 with factoring. This is similar to your zero product law. Does anyone at least remember the zero product law wording? Like me saying that? Does it sound familiar? It's okay if it doesn't. It was how you found the x-intercepts from factoring for when you factored a parabola, or an equation of a parabola, and you factored it, and you found the x-intercepts that way? No, it was so long ago we don't remember it. That's okay. We'll get there. We're going to do it again. This is factored form. Does that at least look like the answers on your Factor Master test? Yes. Okay, so what you're going to do is if you have factored form, you're going to take each one of those factors and you're going to set each of them not equal to 0. So you're going to take x plus 3 not equal to 0 and x minus 2 not equal to 0. And then you're going to solve for x. So you're going to get two answers this time. You'll have one that says x is not allowed to be equal to negative 3. And the other one that says x is not allowed to be equal to 2. All right, so when you do your set notation here, you just put a comma between those numbers. X is not allowed to be equal to negative 3. And then I would just put a comma 2. You could also put the or in there. I don't really care. You could write or x cannot be equal to 2. You could put negative 3 comma 2. That works for me. Just list them off. Okay? All right, last one here. X squared plus 2x. Let's write that one out. X squared plus 2x cannot be equal to 0. Well, that looks a little bit different too. That's not like the first one, because the first one only had one x. This one has two x's. So when you see a problem like this, when there's an x squared in the denominator and another x, you're going to have to factor. This is where the factoring comes in. What kind of factoring would you use here? What do you always try first? Here, we're going to try with GCF. What would be the GCF of this problem? X. So if I factor out an x, what's left in the parentheses? X plus 2. You take that factored form and set it not equal to 0. Then you do what you just did in B. You take each factor, the x, and set it not equal to 0, and the x plus 2, and set it not equal to 0. Sorry, I'm running out of room here. Well, the first one's already solved for you. You don't have to solve anything for that. The other one, you subtract 2 from both sides, and what is x not allowed to be? Negative 2. So you write your set notation the same way as in B. So that's how you do the rational domain. Let's do one or two of the square root ones here. All right, let's do C. Let's skip to C here. For all of these, when you have a square root and you're taking the domain, remember, you take the radicand. And how do you compare it to 0? What symbol do you put there? Greater than or equal to. You don't want negatives, but you can have 0 or positive. So you solve this inequality. I subtract 8. I subtract 8. I get negative 2x is greater than or equal to negative 8. And then I divide by negative 2. Well, what happens here when I divide by negative 2? The sign flips. This turns into less than or equal to 4. So remember the rule. When do you flip an inequality sign? Divide or multiply by a negative. Divide or multiply by a negative. This is your inequality. Well, they want our answers in interval notation. So if you need to, draw your picture on a number line, put a dot at 4. Well, all those x's are less than 4, which is going to the left. So how would you write your interval? What would you put first? Negative infinity, because I have an arrow over here, negative infinity, up to 4, with a square bracket. So you could pick any number that's 4 or smaller to put into that rational function. Okay? You good so far? All right, so here's what we're going to do. That's it for today. I'm going to have